Okay, so let's finish up with the precise definition of a limit. So let me just remind you of what our previous definition was. Okay, so we have the limit as x approaches a of the function f of x equals L means the following. As x approaches a, or gets close to a, f of x gets close to L, right? So f of x then approaches the limit L, right? Assuming that the limit exists and it's a real number. So this is what we've been working with, and it's worked just fine, right? It's been good enough, and we've used it to calculate quite a few limits. All right. The issue, though, is this phrase gets close to, right? What do we mean by getting close to something, right? How you know, as x gets close to a, what does that really mean, right? How close, right? How close is close enough, right? So we want to make that idea a little bit more precise here. Right? What does it mean to get close to something? Right? I mean, informally, we know what it means, right? So, you know, x approaches 5 just means x is getting close to 5, right? So that, you know, that could mean x is, you know, 5.003, or x might be 4.99996. Right? These are very close to the number 5, right? Oops, 9's here. But are they close enough? Right? In some cases, they might be perfectly close enough. In other cases, they might not be close enough, and you might have to get closer. Right? So you might have 4.999999. 9. So, right, so is this close enough? Most likely, yes, but, you know, it might still not be close enough. Right? So we really need to answer the question, right, how close? Right? So that's what this epsilon delta business is going to be, right? So let's get to the more precise definition here. Okay, so now we have the limit as x approaches a of f of x is equal to L, right? L being the limit if it's a real number. So here's what that means. If for any positive number epsilon, right, so this little symbol here is the Greek letter epsilon, there is a corresponding positive number delta. This is the Greek letter delta, so that f of x minus L in absolute value, right, is less than epsilon whenever x minus a in absolute value is positive and less than delta. Okay, so let's untangle what all that means, because this is, I realize this is very confusing at first. So let's draw a picture, because that always helps. In this case, I'm going to draw the graph of some function. At this point, it doesn't matter what function that is, just as long as it's some function. So here's my f of x, right? And so a is going to be, let's say, right here. So that's my a. And we can see what L is going to be. L is going to be the corresponding y value here, right? And remember, so this function is continuous, so of course f of a is equal to L, but it doesn't have to be. In fact, if you want to put a little hole here, that's fine too, right? Because that doesn't affect the limit. Okay, right? So, informally, as x approaches a, let's say from the left, then f of x, the y-coordinates, approach L. Right? If f of x approaches A from the right, once again, the y-coordinates approach L. Okay. So that's the previous definition. That's the one we've been working with, the one that's been good enough. Okay, so now we want to make this a little more precise, right? The idea is we want to make sure that our f of x is close to L. How close? Epsilon close, right? That means it has to be within epsilon. So I'm going to make this point here, this number here, L plus epsilon. And down here, this will be L minus epsilon. Okay, so any y value between, right, L minus epsilon and L plus epsilon, right? So that could be our f of x anywhere in there, right? So let's see, f of x is right about here in red. I hope you can see that, right? So as long as f of x is anywhere in this band, here, let me erase that, anywhere in this yellow band here, that's all we need. Okay, so what's gonna guarantee that that's gonna happen, right? So I need x to be close to A. Well, how close, right? I mean, what could be my x so that f of x is within this band, is between L minus epsilon and L plus epsilon? Well, let's say my x is over here, right? That's pretty close to A, right? I'm not that far from A. But then up here is my f of x. And you can see that that's not between L minus epsilon and L plus epsilon. So this x is not close enough, right? This x that I drew here is too far away from A so that the f of x is not within this band, this L minus epsilon to L plus epsilon band, right? So I need to pick an x that's even closer, right? Let's say I pick x to be over here, right? So that's even closer. That's pretty close to A. Is that close enough? Well, where's my f of x? My f of x is right about here. That's the y-coordinate, and let's see, is it within that band? Just barely, but yes, it is. Okay, so that x is close enough. Okay, so what we need is x to be close enough to A, erase all this, so that f of x is within epsilon, right, of L, of the limit. Right. So here's what I need, right? Here's L minus epsilon. If I go straight across and then I go straight down, pretend that's straight down, right? And I take L plus epsilon, I go straight across and then straight down. Make it a little straighter. Close enough, right? So now you can see where x has to be. X has to be within this band here. I'll make it a little blue band here, right? So as long as x is anywhere around here, right, then the corresponding f of x, right, so if this is my x right here, then my f of x is guaranteed to be within epsilon of L. Okay, so I just need to pick a delta, right, so that my distance from A, right, A plus delta and A minus delta, right, if my x is within that band, that's going to guarantee that my f of x is not too far away from L, is within a distance of epsilon from L. Okay, so that's the idea of this definition, right? It makes a lot more precise the idea of, well, x is getting close to A, that forces f of x to get close to L, right? But now we want to say, well, how close do we need to be, right? So x has to be within delta of a for f of x to be within epsilon of L. Okay, let me say that one more time, right? X has to be within this band. It has to be right between a minus delta and a plus delta, right? For f of x to be inside of L minus epsilon to L plus epsilon. Okay. And yeah, effectively this just means that x minus a in absolute value has to be less than delta, right? And the reason why this has to be positive, right? If this were to equal 0, then x would equal a. And remember, we don't care what happens when x equals a, right? The limit doesn't care what happens when x equals a. So yeah, we don't want x to be equal to a. So that inequality here, right? That strict inequality ensures that x cannot be equal to a, right? But it still has to be close to a. And this is how close it has to be. It has to be within delta of a, right? And then this just ensures that f of x is close enough to L within epsilon. Okay, so that's the formal definition of a limit, right? It's a more precise definition. All right. So let's see an example of that. Okay, so our first example, f of x is just 5x minus 3, and we want to find the limit as x approaches 2 of f of x. Right. In fact, I'll let you do that. Right? So, you know, you're not going to make a table of values. You're not going to draw a graph. I mean, you can, but the easiest way to do this is to recognize that this function, 5x minus 3, is a linear function. So it's a polynomial, and all polynomials are continuous. So because we know it's continuous, we know that the limit has to be equal to f of 2. So just plug in 2. 10 minus 3 is 7. Okay, so the limit is 7. Right? You know, that's about as easy as it gets here when finding limits. So we know L is 7. Right? That's our L. Right? And we know A is 2. Right? Remember, x approaches a, so a is 2. Okay. So what we want to do is prove that this is the case, right? We want to prove without any doubt that as x gets close enough to 2, that f of x, 5x minus 3, gets closer and closer to the number 7. And we're going to use the precise definition to show that, right? What we need to show, right, and here it is again, that f of x minus L is less than epsilon whenever 0 is less than x minus a, which is less than delta. Okay, so let's plug in what we know now, right? Yeah. So we know that f of x is 5x minus 3. 5x minus 3. And L we know is 7. So that has to be less than epsilon whenever 0 is less than the absolute value of x minus a. Remember, a here is 2, is less than delta. Okay, so in order to show this, right, what we need, right, we need to find a delta, right, positive number delta, which could, of course, depend on epsilon, right? So this might depend on epsilon, but it cannot depend on x. It can only depend on epsilon, right, in some way. So we need to find that delta so that that absolute value of 5x minus 3 minus 7, so that's just 5x minus 10, is less than epsilon. Right. So we want to guarantee that this f of x minus L, right, is within epsilon. Okay, so what should our delta be here? Okay, so let's look at this more carefully, right? 5x minus 10 in absolute value. If I factor out the 5, right, I get 5 times x minus 2 in absolute value is less than epsilon. And if you remember anything about absolute value, right, when you take the absolute value of a product, right, you can split it up. So you can take the absolute value of 5, which is 5, times the absolute value of x minus 2. And that has to be less than epsilon. So, right, if you notice, this is very similar to this. Absolute value of x minus 2 is less than delta. The only thing is I don't have a 5 on the left. So, easy fix there, just divide by 5 on both sides. Right? So that cancels the 5. And now what I'm left with is absolute value of x minus 2 is less than epsilon over 5. Well, that has to be my delta then. Right? So we're going to choose delta to be equal to epsilon divided by 5. Okay, so by making that choice, right, let's see what happens. Right? If delta is epsilon over 5, right, that means that x minus 2 in absolute value, right, has to be less than epsilon over 5. Okay, so if that's the case, is it true that f of x minus L is less than epsilon? That's what we need to show. Well, again, we know what f of x is, right? 5x minus 3, sorry. I almost forgot. And we know what L is, right? We calculated the limit. It's just 7. Right? So is that less than epsilon? Question? Well, let's see. This is an absolute value 5x minus 10. And we still don't know for sure if that's less than epsilon. But we know that this is equal to 5 times the absolute value of x minus 2. But remember, the absolute value of x minus 2 has to be less than epsilon over 5. Right? So this is equal to epsilon. Right? Which is not less than epsilon, that's true, but it can be as close as you want. Right? So yeah, this looks a little funny. Epsilon is less than epsilon. We know that's not true, but it's just an equivalent condition. Right? In other words, x minus 2 is less than delta, and remember we said that delta is epsilon over 5. Right? If you just multiply both sides by 5, right, working backwards, and then pull the 5 inside, right? And, you know, 5x minus 10 is the same as 5x minus 3 minus 7. And this is my f of x, and this is my L. Right. So, sorry, L is positive 7. Right, so I'm subtracting. So this is f of x minus L, and that has to be less than epsilon. And that's what we wanted to show. Okay. So there you go. We just proved that the limit as x approaches 2 of the function 5x minus 3, right, that has to equal 7. So if you didn't follow all that, don't worry about it, right? This is not that big of a deal, right? After all, we calculated the limit in many ways already. We used a table, we drew the graph, and we used continuity, right? We used that the function is continuous, and we can calculate the limit just algebraically by plugging in 2. Again, the only reason why we can plug in the 2 here for x is because we know it's a continuous function. So that allows us to calculate the limit a lot more simply. So this epsilon delta business just makes it much more precise. Okay. Right. So I'm gonna do an even harder example. Right. This is a relatively simple one. All right. So the more difficult example, we want to show that the limit as x approaches 1 of x squared plus 3x equals 4. Right. Again, pretty obvious, right? I mean, x squared plus 3x, quadratic function, it's a polynomial. So the way you calculate a limit is just plug it in because we know it's continuous. And 1 plus 3 is 4. Okay, so finding the limit is not that hard. At least I hope not. But proving that that's the limit using epsilon delta, so this one's going to be a little bit trickier. Okay. So remember what we need to show, right? In fact, what we need to do, we need to find a delta which will depend on epsilon, although it doesn't have to, but it usually does. Right? So that delta will be some positive number, right? So that if the absolute value of x minus 1 is less than that delta, then that guarantees that the f of x minus L will be less than epsilon. So in this case, f of x is x squared plus 3x, and L is 4. Okay. So how are we going to find this delta, right? All right, so one thing to notice is this x squared plus 3x minus 4. That's also sorry, I'm trying to factor this in my head here, right? I think it's x plus 4 times x minus 1. Yep. Okay, just checking. Right, we have 4x minus x is 3x. Good. Okay. And this is also the same thing as absolute value of x plus 4 times the absolute value of x minus 1. Okay. So notice that this absolute value of x minus 1 is the thing that should be less than delta. Right? So as long as that's less than delta, the x minus 1 is less than delta, then this whole thing should be less than epsilon. Okay, but remember that epsilon, or rather delta, should not depend on x. It can depend on epsilon. So, right, the easiest thing you might want to do is just divide by the absolute value of x plus 4 on both sides. Right, so then you get the absolute value of x minus 1 is less than epsilon over the absolute value of x plus 4. Now that would be nice, but now our delta would depend on both epsilon and x. And we cannot have that happen. So yeah, this is why this is going to be a little trickier. It's going to be a little bit subtle, right? So here's where I'm just kind of play around with this a little bit. I'm going to say, look, I need to pick a delta that's small enough, and I don't know exactly what small enough is, so I'm going to make up a number. Let's just say it's 1. Right? Let's say my delta is 1. Right? So that's pretty small. I mean, you can imagine getting smaller than that. But, let's just start with 1 and see what happens, right? So what that means is my absolute value of x minus 1 has to be less than delta, but I just said that delta is 1. Okay, so that means in absolute value, if I want to get rid of the absolute value, right, x minus 1 has to be between -1 and 1. Oops, I put it, yeah, there we go. So if I add 1 to the left and the right and the middle, I get that 0 is less than x is less than 2. So if my delta is 1, that means x has to be somewhere between 0 and 2. Okay. Now, what does that mean for this other factor here, this x plus 4? Right? Well, if x is between 0 and 2, then if I add 4 to everything, the left side and the right side, right, I get that x plus 4 has to be bigger than 4, but less than 6. Okay. Right? And in fact, right, because the 4 is smaller, the absolute value of x plus 4, well, that has to be less than 6. Right? That has to be less than 6. And even though, right, this is going to allow numbers that are, less than 4 here. Right, again, remember, we just want to guarantee that x plus 4 is less than 6. So if the absolute value of x plus 4 is less than 6, that's good enough. Okay. So now, if my x plus 4 is less than 6 in absolute value, my x plus 4 times x minus 1 is going to be less than 6 times absolute value of x minus 1. Remember, we want that to be less than epsilon. So now, just divide by 6. And what that tells us is that the absolute value of x minus 1 is less than epsilon over 6. And we want x minus 1 to be less than delta, so we have our delta, right? It should be epsilon over 6. Now wait a minute, right? Didn't earlier I say that delta is just 1? Well, it could have been 1. I mean, that was my choice. But using this argument, it's pretty clear that we want delta to be epsilon over 6, depending on what epsilon is, right? So I want delta to be as small as possible. So I'm going to choose the smaller of the two values, right? Pick delta to be the minimum of either 1 or epsilon over 6. So we can write that as just the minimum of the set of numbers 1 epsilon over 6. Whichever one is smaller should be good enough. Okay. All right, so again, that's might not be clear at this point. But let's see what happens, right? Let's see what happens, first of all, if, right, our delta is epsilon over 6. Right? So that means that in absolute value, my x minus 1 is less than delta, or in this case, epsilon over 6. Right? And we know that we can multiply both sides by 6. Right? And we also know that, right, because of this argument, my x plus 4 in absolute value has to be less than 6, right? So, right, so this has to be less than, absolute value of x plus 4. So that has to be less than epsilon as well. And then when you combine everything, you get that absolute value of x squared plus 3x minus 4 is less than epsilon. And this should be familiar, right? This part here is the f of x squared plus 3x, and minus 4. 4 is the limit. 4 is the L. So that's what we needed to show. Okay, so that should do it. As long as my delta is either 1 or epsilon over 6, whichever one is smaller, that's going to guarantee this. Okay? And that proves that this limit, the limit as x approaches 1 of x squared plus 3x equals 4. All right, again, don't worry too much about the details here. If you didn't quite follow everything, I really wouldn't worry about it. It's this is highly technical, right? This epsilon delta business here really is more for an advanced calculus course or a real analysis course. So if you are interested in, in the more abstract mathematics, and you want to take, more math courses, eventually you're going to have to do this, right? But for most purposes, especially if you're going into engineering, you're probably not going to use this. So in that case, I wouldn't worry too much about it. So just to continue with this example, and this might help, figure things out a little bit. Let's give an actual value to epsilon, right? Let's say we want our f of x minus L to be less than some. Let's make it a small number here. Well, let's actually just make it 6, right? In which case delta is 1 anyway, right? So suppose, let's write this here. Suppose epsilon is 6, which again is not that small of a number, but it's small enough, right? So in that case, delta is going to be the minimum of 1 or 1, so we know delta has to be 1. Okay. So if delta is 1, right, is x going to be close enough, right? If this is true, does that guarantee that my f of x minus L is less than epsilon? Is that true? Okay, so let's check. Remember, f of x was x squared plus 3x. The limit was 4. Is that going to be less than epsilon? Oh, epsilon in this case is 6, right? Is this going to be less than 6? All right, that should be a 6. Because that was my choice. Okay. Well, remember what absolute value is. It just means that this whole function here, x squared plus 3x minus 4, be a 3x minus 4, that has to be between -6 and 6. And now, if we just add 4 to everything, plus 4, we get that x squared plus 3x is between -2 and 10. Right, so that's my f of x here, right? F of x has to be between 10 and -2. Right. So in fact, the limit here, remember, was 4. So let's draw a picture here. So if 4 is in the middle and epsilon is 6, right? So 4 plus 6, that gives us the 10. And then 4 minus 6, that gives us the -2. Okay, so we want to guarantee that f of x is between -2 and 10. So how can I do that? Well, I have to make sure that, right, x is not too far away from 1, right? 1 is the a here. A was 1. Oh. Right. So is it the case that if x minus 1 in absolute value is less than 1, and remember that just means x is between 0 and 2, right? Is that enough to guarantee that f of x is between negative 2 and 10? Okay, so this is where a picture really helps. So I'm going to try to draw the graph here as best as I can. So this is 1, 2, 3, good enough. And I'm going to squash the scale a little bit here, right? So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we know we have to go up to 10, and here's negative 2. So the graph of f of x is going to look something like this. And yes, when you plug in 2, you do get exactly 10. That's kind of the point here. If I plug in negative 1, I get, yeah, negative 2. So the parabola looks a little bit like this. Okay. So here's a equals 1, right? Remember, we want x to be close to 1, approaching 1. And we know L is equal to 4. And I set my epsilon pretty large, right? I set my epsilon to be 6. So as long as f of x is between, right, 4 plus 6, which is the 10, and 4 minus 6, which is the negative 2, we want f of x to be somewhere in this band, right? So what happens if x is between 0 and 2? In other words, my delta, remember, I set to be, or I chose to be equal to 1. And if delta is 1, then x has to be between 0 and 2. So if I pick any x between 0 and 2, right, is my f of x guaranteed to be somewhere between negative 2 and 10? And you can see what happens, right? So what's the smallest f of x will be? F of x will be, well, 0, right? F of 0 is 0, which is certainly bigger than negative 2, right? And what's my biggest x I could be? Well, actually, it can't be 2, right? X has to be less than 2. So, okay, pick your x to be, 1.999. That's still less than 2, right? And now, if I go up on the graph, where do I end up? What is f of 1.999? Okay, so it's going to be somewhere close to 10. So it's going to be, let's see, about 9.993. Yeah, less than 10. Right, and I can get even closer to 2, right? Even if I make it all the way to 2, right, it's going to be exactly 10. So as long as x is less than 2, f of x will be less than 10. So in other words, I will be within this band here. Right. In fact, I could go all the way down to negative 2, but it's, right, as long as I'm between negative 2 and 2, and in fact, I'll be between 0 and 10, then this delta was good enough. So delta equals 1 is enough for epsilon equals 6. Okay. Right. All right, so yeah, but the point is, right, the whole idea of a limit is that I want f of x to be close to L, right? I want x squared plus 3x to be close to 4. So is 6 away close enough? Well, probably not, right? So let's make epsilon something smaller. Let's make epsilon, let's say 0.6. Okay, so this is our given epsilon. Right. Our job is to find a corresponding delta, right, such that when x minus 1 is less than that delta in absolute value, then that guarantees that my f of x will be pretty close to 4, within epsilon, within 0.6. So let's see how that works, right? So remember what our delta was. It's the minimum of 1 and epsilon over 6. Oops. So if epsilon is 0.6, then that divided by 6 is 0.1. Right? So I want my delta then to be 0.1. So I'm going to have to choose delta to be 0.1, right, which is less than 1. So it's the minimum of 1 and 0.1. So 0.1 being the smaller number, that's the one I'm going to choose. Okay, so if I do that, my x minus 1 has to be less than delta, less than 0.1. And that means that x is between 0.9 and 1.1. Okay, so as long as x is within that interval, right, does this guarantee that my f of x minus L will be less than epsilon? Or in this particular case, my x squared plus 3x minus 4, will that be less than 0.6? Okay, so let's see if that works, right? If I take 0.6, that has negative 0.6, that's going to be less than x squared plus 3x minus 4, and that has to be less than 0.6. So add 4 to everything. And so we're going to get 4 minus 0.6, I think that's 3.4, is less than x squared plus 3x minus 4.6. So, right, there's my f of x. My f of x had better be between 4.6 and 3.4. Okay, so, right, so that's the guarantee that we want. We want f of x to be in that interval. So if my x is between 0.9 and 1.1, that should guarantee that f of x is between 3.4 and 4.6. Right. Are you convinced of that? Do you buy that, or is that still not clear? Right. So again, look at the picture. Right. It's I'm going to sort of expand this out a little bit. So here's my 1, and let's pretend that this is 1.1 and 0.9. So my x has to be on this interval between 0.9 and 1.1. So pick any x in that interval. And then my f of x, some curve like this. Right? Remember, when x is 1, y is 4. And we want to guarantee that, right, f of x is between 4.6 and 3.4. So, sure enough, if I pick an x on that interval anywhere in here, that's going to guarantee that my f of x is within this band, from 3.4 to 4.6. And I think my picture's a little backwards here, because the way I drew it, it's not sufficient. Yeah, so let me try to fix that. Okay. So I think I had it backwards. So this should be my, oops, sorry, 3.4. It should be somewhere down here. And my 4.6 should be somewhere up here. Yes. Okay. There we go. Now it's right. Right. So if I pick x to be as far away from 1 as I can be, right? Remember, it has to be within 0.1. So the furthest I can go is 0.9 to the left and 1.1 to the right. But even if I go that far, even if I plug in 0.9, whatever my y value should be, it should be bigger than 3.4. Right? We know it's less than 4.6, but it's got to be bigger than 3.4. So, yep, so 0.9 squared plus 3 times 0.9. What is that? Sorry, calculator. I think it's 3.51. So, yep, that's certainly bigger than 3.4. Right, and even if I pick 1.1, so 1.1 squared plus 3 times 1.1, and that's going to be 4.51. And that's less than 4.6. Okay. So, yep, no matter what x I pick, between 0.9 and 1.1, anywhere in this band here, that's going to guarantee that my f of x is not going to be further away from 4 than 0.6. In fact, it'll even be less than that, but that's okay, as long as it's not bigger than 0.6. All right. Right, so that should do it. Right, so this is the idea of the epsilon-delta definition. It's a lot easier, of course, when you have a linear function. Once you have a quadratic, then you have to do this sort of minimum thing, which, again, is a little confusing. But realize that it works. We did this example, and it looks like it works. So I'll do one more, kind of an easier one. I'll go back to a linear function, and then that should do it. Okay, last example. We want to show that the limit as x approaches 9 of 1/3 x plus 2 is equal to 5 using epsilon delta. Right, so it should be clear, right, that this limit is 5. We get, right, 1/3 of 9 is 3, 3 plus 2 is 5. But again, the hard part is showing it rigorously using epsilon delta. Okay, so here's the definition, right? In fact, let me just write it down in general. Limit as x approaches a of f of x equals L. This means the same thing as, oops, I don't want to use an arrow. So, all right, this means that for any given epsilon greater than 0, there is a delta also greater than 0, such that if I take the absolute value of f of x minus L to be less than epsilon, that has to be true whenever 0 is less than absolute value of x minus a, which is less than epsilon, right? So what do we have here? We know that f of x is 1/3 times x and then plus 2. We know that L is 5. We know that a is 9. Okay, so we're going to be given an epsilon, right? And in fact, we could put in a number here, right? We could make epsilon, say, 0.05 or something, but we'll do that later. Let's just leave it as epsilon, as long as it's some positive number, right? And we need to guarantee that f of x, that is 1/3 x plus 2, minus L, right? L is 5, that has to be less than epsilon. So we need to pick a delta greater than 0 so that this happens. Well, in absolute value, right, 1/3 x plus 2 minus 5 is just -3, and that's less than epsilon. And if I factor out the 1/3, right, I get 3 times 3 is 9, so absolute value of x minus 9 is less than epsilon. So if I just multiply both sides by 3, right, cancel the 3's on the left, and now I have absolute value of x minus 9 is less than 3 times epsilon. Right, but remember, a is 9, and we want absolute value of x minus 9 to be less than delta, So that has to be my delta, 3 times epsilon. So we have to choose our delta to be equal to 3 epsilon, right? Or anything smaller than that, right? That's as big as we can make it, right? We don't want to make it any bigger. Right? We don't want to make it 4 epsilon, right? Or 3 epsilon plus 2. But we can always make it smaller than we want. But for now, let's just make it 3 epsilon. So that's sort of the largest we can make our delta in this, for this to work. Okay. So now let's just use the same argument backwards, right? If our delta is 3 epsilon, so if x minus 9 in absolute value is less than 3 times epsilon, right? That means I can divide both sides by 3. And I have 1/3 times x minus 9 in absolute value is less than epsilon. Or bringing the 1/3 inside, this is 1/3 x minus 3 is less than epsilon. And now we just have to split it up into the f of x part. F of x, remember, was 1/3 x plus 2. So to make -3, I have to subtract 5. And there you go, right? This is my f of x minus my L. Oops. And that is less than epsilon, guaranteed. So as long as my delta is 3 times epsilon, or smaller than that, then my f of x will be within epsilon of L, of 5. Okay. So that's all this is. Yeah, as I said, in practice, I'm much more concerned that you know how to calculate the limit, just using the rules of limits, or using a table, or using a graph, right? So that's the important thing in this chapter, is being able to calculate limits and understand what limits are and how they differ from just, plugging in 9. Again, you could have just plugged in 9, but only because we know that this is a continuous function at x equals 9. Okay, so this epsilon delta is just a more precise way to say, well, as x gets close to 9, okay, how close? Delta close, right, within delta. Then f of x, the 1/3 x plus 2, will be very close to 5. How close? Within epsilon. Right. So that's the idea.